session, and I'm Raya Hadsel. I'm going to be the session chair. The first spotlight is going to be on robust subspace estimation in a stream, and it will be presented by Roe Levin.
Hello, welcome to my talk. My name is Roe. I'll be talking about robust subspace estimation in a stream. This is joint work with Anish Sevekhari and David Woodruff. All of us are from CMU. So I have about enough time to tell you what the title means. So what's the problem we're solving? This is the problem we're not solving. We're given a set of n data points, okay, that live in RD and a target dimension k. And the goal is to output a k-dimensional subspace of RD such that we minimize this sum of squared distances of each point to the subspace, okay? And the notion of distance we're using is the standard Euclidean distance. So this is a classic problem, and we're going to study one robust version of this problem. So we're going to replace the square term with just the distance. So we're minimizing the sum of distances to our subspace. And what does in a stream mean? It means that we never see the data like all up front. We're given the data points one by one in a stream. And the hard part here is to solve the problem in sublinear space. Okay? And in fact, our algorithm is going to work in what's called the general turnstile streaming model. So we actually don't even need to see the points one by one. We're OK with arbitrary, like entry-wise additions and subtractions to those data points. So pictorially, it looks something like this. And we're going to write this objective as this low-rank approximation problem with this thing I'm calling the 2-1 norm. This weird thing. It's easy to work out. It would take you about a minute, but basically it's this norm means that you take a matrix and you take the L2 norm of each row and then you sum these. Okay, so you can basically just express this problem this way. So in 2015, Clarkson and Woodruff showed that the offline version of this problem is NP hard to approximate to within a 1 plus 1 over poly d factor. Okay? So surprisingly, this is a very hard problem. And particularly, this implies if you want a 1 plus epsilon approximation algorithm, you can't hope for a polytime algorithm. So on the flip side, they do give a 1 plus epsilon approximation algorithm. Okay, and the key here is that they spend time exponential in a polynomial in k over epsilon. Okay, so this is still a big win because it's not exponential in n or d. So n is the number of points and d is the dimension. Okay, and other than this exponential term, the leading order term is n and z of a, which means number of non-zero entries of a. Okay, so this is a very, very fast algorithm. Okay, so what do? We show that there is a 1 plus epsilon approximation algorithm to the same problem with the following guarantees. It runs in the turnstile streaming model with sublinear space. And furthermore, if you run it offline, which is kind of the only way it makes sense to make a time comparison, it's actually the same as the Clarkson-Woodruff algorithm up to the leading order terms. So in the minute or so I have left, let me try to give you a very sketchy version of how we do this. So we're given this problem, and we don't know what to do about this weird norm. We don't know how to solve this minimization problem. So what we're going to do is we're going to reduce the problem to a different problem, hopefully with smaller dimensions, okay? So we're going to somehow pick these y and z that are functions of a. And believe me that you can brute force the solution in time that's exponential in the dimension. This is not straightforward, but one can show this. So now I claim if we show three things, we'll have shown our claim. The first is that the solution below is indeed a 1 plus epsilon approximate solution to the first problem. The second is that f1 and f2, these functions are what's called oblivious linear sketches, which means that they're linear functions, and so they're matrices, and the entries of this matrix does not depend on A. Okay, which means that we can compute these matrices without even seeing A in the first place, and then exploit linearity as every incoming data point comes in. We apply this matrix to that data point and add it to what we've seen before. Okay. And finally, if the dimensions of y and z are small, so polynomial in k over epsilon, then we indeed get this time that's exponential in polynomial in poly k over epsilon. Okay, so just to wrap up, we have some experiments on both synthetic data, so we can construct examples where our algorithm does arbitrarily better than the first thing you would try, which is the like truncated SVD, as well as some real-world data. So thanks, that's just about my time. Thank you. Oh, come see me at the poster.